Okay, so today we will start with the effect of sun intensity on the solar generation. But before that, last time we have completed till effect of climate, and we have seen that if it is a partially cloudy day, then the PV module can produce up to 80% of uh, full energy. I mean, suppose there is no clouds are there and sun is clear. In that case, suppose we are getting 100% of energy. Then during partially cloudy day, almost we get 80% of the energy. So even on extremely overcast day, it can produce up to 30% of the power. One more important aspect is the solar panels are designed in such a way that snow does not get collected on the module because we provide tilt angle to them. So, snow is not accumulated, but automatically it falls down to catch the sun angle. Okay, and mechanically also modules are designed so sturdily that it withstand the golf size hail. Hail means आपण गारांचा पाऊस म्हणतो ना, तसा गारांचा पाऊस जरी पडला तरी सुद्धा सोलर पॅनल्स कॅन विथस्टँड दॅट मच अमाउंट ऑफ प्रेशर imposed by the hills, snow hills, because mechanically it is made very strong. Now, coming to the next point, which I want to discuss technically with the help of graph, is the sun intensity. So, you know what is intensity? Power per unit area of solar irradiations. So power is watt, per unit area is meter square. So watt per meter square is the unit for solar irradiations. So intensity is solar irradiations per unit area. So higher the intensity, definitely we will get more current from the panel and we will achieve more power. Current is more, so we can extract more power from the solar panel. So here I have taken an example, say 0.25 sun means what? It is clouded or some shadows are coming and we are getting only 25% of solar irradiations. Then let us say this is the curve wherein we are getting only 0.25 ampere of current. If we get zero point 0.5 of sun, we get this much amount of current. Likewise, a more the intensity, more the current we can get. So our IV characteristics remain same, only it gets shifted upwards with increase in intensity. Now, one more aspect is the efficiency. So here I have drawn a graph of photovoltaic efficiency with respect to sun intensity. So you can see here, this is the graph representing the efficiency with respect to sun intensity. So efficiency of the panel remains same within a particular zone of intensity. So here, if we consider 500 to 1000 watt per meter square sun intensity, then there is not a much variation in the efficiency. It is almost constant. So you can say this is the optimistic way of operating the solar panels. I mean, ideally, we should operate it in such a way that at least our panel should get minimum, in this example, 500 watt per meter square solar intensity, and it will vary till say 1000 or more than that. It will not affect much on the efficiency of the system, and we can achieve better solution. Okay, now next point is the sun angle. So sun angle, actually it is a tilt angle that we give to the panel so that our panel will always face to the sun and we can extract maximum amount of solar power. So here I is equal to I0 cos theta. So I is the current that we achieve from the solar system. I0 is the current with normal position of the sun. So normal position means we are considering the starting point, that is during sunrise at east. So obviously the angle between the panel and the sun will be 0 at that time. So here theta will be 0, cos theta will be 1, and our current is equal to I0. So whatever is the current that we get initially, that we called as I0. And as sun travels from east to west, or say east to mid afternoon, we get maximum power during mid afternoon around 12 to 1, right? So at 90 degree, we expect maximum amount of power extraction from the sun. So here I have shown you a sine curve and a cos curve, cosine curve, right? So blue indicates a sine wave, and this red indicates the cos wave. So here we are interested mainly from 0 to 90 degree, wherein our power goes on increasing, right? So at 90 degree, sun is on the top of the head. Sorry, sun is, yes, at 12 noon. At 12 noon, we get maximum amount of energy. So this formula I equal to I0 cos theta, here we are considering theta to be mathematical theta, trigonometric cos theta, right? Cosine theta. But for solar generation, this does not hold good with mathematical cosine, but there is another constant which is called as the Cayley constant, which Cayley has defined. So if we find out the angle, cosine of the angle at 30 degree, it is 0.866 with mathematical cosine. But with Cayley constant, it becomes 0.866, which is same for 30 degree. But from 50 degree onwards, we are interested in 90 degree because at 90 degree, mathematical cosine will become 0. So at 50 degree, you can observe it is no more 0.643, same as that of mathematical cosine, but it is decreased. It is 0.635. At 60 degree, mathematical cosine is zero point 0.5, but Cayley constant is 0.45. At 80, it is 0.174, whereas it is zero point 0.1. And at 85, Cayley says that the constant value becomes 0. So if we see the graph, cosine graph, Cayley cosine graph, if we see the Cayley cosine graph, then its zero crossing point is not at 90 degree, but it is at 85. But it is 85, and hence this makes a sense that it is no more equal as that of the mathematical cosine, but it depends on the Cayley constant value. So we get maximum power when, now see here we are saying 0 because every time actually we want to make the angle 0, and that's why we are saying MPPT control. We are using MPPT controller. Now question will come to your mind that when sun rises, at that time we are not getting maximum power, but we are getting maximum power when sun is at 12 noon, when we get maximum heat and light energy, right? So how is it possible at 90 degree? It is showing 0, right? So this is the angle made. I mean, if we make the panel fixed at say 0 degree, it will face. So it will be vertical, right? Suppose sun is coming at extreme right. So here is a sun and we want to face it to the panel. Then we will keep the panel vertical. At that time, the angle will be 0 because sun is facing to the panel. And if we make it stationary and we do not move it, then definitely at 90 degree, it is not going to catch any power and the total current will be 0. So from that angle it is given, but that's why we are tilting our panel to get the maximum solar extraction. Okay. If you have any doubts, you keep it aside. We will solve it at the end of the session. Now the next is electrical load matching. So it is one more important concept which we have to take into consideration. So generally it is divided for two types of load. One is with resistive load and another is with the constant power load. So in electrical load matching, when we take example of electrical load matching with resistive load, then I have shown here IV and PV characteristics which we are familiar with. We already have discussed about the IV characteristics and PV characteristics of solar cell. So here this pink line shows the IV and PV characteristics. We have considered three loads R3, R2 and R1, considering R1 is the smallest load and R3 is the largest load among the three. So for resistance R3, it is say drawing the current I1 and operating point is A1. Okay, on IV characteristics. For R2, the current is I2 and operating point is A2. Whereas for R3, the current is I3 and operating point is A3. Now same points I have tried to show on the PV characteristics with R1 load I1 current, R2 load I2 current and R3 load I3 current. Now looking at the characteristics, even you can decide that we get maximum power at point A2. That means with the load R2. Because this is the power characteristics. You can see here whatever we are getting, here whatever we are getting, and here whatever power we are getting. Generally, here we get the maximum power. So, likewise, when we install a particular system, in that case, we should first observe the IV and PV characteristics. Okay, we should simulate the IV PV characteristics and decide the point of operation. So, ideally, we should keep the load on the system in such a way that it will operate in a middle zone of the PV characteristics so as to extract the maximum power. Okay. So likewise, we have different curves for different loading conditions. So we have to take care that the load should be such that the loading amount should be such that we will always extract the maximum amount of power. So this was for resistive load. Now we'll see the constant power loading condition, which is very interesting. So constant power. So we have two operating points here, B1 and B2. Okay. So with corresponding P1 and P2. So here for P2, I mean the load is of P2 say, then we can achieve P2 at point B1 also, at point B2 also. At point B1 we have less voltage, high current, whereas at point B2 we have high voltage, less current, right? But the product of V and I, which is the power, is same at both the operating points B1 and B2. I have shown it with a pink line, B1 and B2 on IV characteristics. Also on PV characteristics, I have shown B1 and B2 where power corresponds to P2. Okay, so you can operate the system at B1 or B2, both, for getting the same power. But again, considering the stability of the system, okay, and using controllers and all, it is suggested that always B2 is the point where you should operate the system to become more stable with shortest amount of time. It means you might have studied in PSOC, power system operation and control, and also in your PS2, that whenever any transient occurs on the system, we need to make the system stable with a stable operating point. Then, in case of transients, it is observed that rather than operating the system at point B1, it is always beneficial to operate it at the B2 considering the transients coming on it. Okay, because point B2 is more stable as compared to that of point B1. Okay, I mean the restoration of the system takes place very fast at the point B2 whenever any fault occurs. So here we have completed all the parameters which are affecting on the solar power generation. Now the last part of the system, which is standalone and grid tied solar system. So today I'll explain you the block diagram only, and next time we will directly move with a example. I'll explain you how to design the rooftop solar system with and without grid tied system or a standalone. So till that time, all of you keep the light bill of your residential ready, and also you start calculating the load in your home, because you have to solve one assignment on designing of the solar rooftop system. Okay, till the next lecture Monday. So let us come back to the block diagram of a solar system. So here this is a rooftop solar panel. So we are interested to design the number of panels with specification of each panel. So once we get a solar energy from here, obviously it is going to be a DC power. So there is a charge controller. The function of the charge controller is to maintain the correct amount of voltage. It also acts as a stabilizer. So this is used for charging a battery. It does not allow the overcharging and under discharge of a battery, because see again we have a one lesson in detail on batteries also. So you will understand that battery have a limit To charge above a certain limit, it cannot be charged more, otherwise battery life gets hampered. And below a certain point, you cannot discharge the battery, otherwise it is difficult to again charge it. So to control these extreme minimum and maximum points of the battery, charge controller plays a vital role. Also, it acts as a stabilizer which stably provides a constant voltage source to the battery. Okay. Now this is a stored power in a battery, which is DC. So DC is converted to the AC with the help of inverter. Nowadays, inverter and charge controller both comes together. I mean, both the functionalities are given provided in a single device. So once it becomes AC, then we can use it at a domestic application wherever we want it. Okay. Or otherwise, if it is excess power, then we can give it to the national grid. So when it is standalone system, then we are not connecting it to the grid, but we are only using it for the residential applications. But again, 100% of the energy is not received from the solar. But whenever we have high demand, that time the excess power which is not supplied by the rooftop solar PV, we can take it from the grid. Okay. And when the power requirement is less, which is sufficiently provided by the rooftop solar PV, we can first always, I mean, the priority is such that we always use the generated power first, and if excess demand is there, then only we are getting it from the grid. So whenever we take the power from the grid, it is called as import. Whenever we give our energy to the grid, it is called as the export. So in is import, out is export. Okay. So this way, you can have a grid tied and standalone system. Only in case of grid tied system, we have to maintain the conditions for tying the grid, which you already have studied in PS2, PSOC, where there are specific conditions while putting the generator in parallel. So this is nothing but it is as good as a generator as we are generating the power, and that we are putting in parallel with the grid. Now see the concept of net metering or the import export which we have discussed just now. Coming power in to the home is called as import. The generated power at our home, if we are giving it to the grid, then it is called as the export. We are exporting the power like that. Okay, so see here, this is a very nice diagram. Briefly, everything has been given. So these are the solar panels which convert the solar energy into electricity. That electricity comes to the home with the help of charge controller and inverter. Okay, so DC is converted to the AC. It is coming to the home. So we are using the power at home, whatever AC appliances we always connect. Then, if we have excess power, we will give it to a grid using a bidirectional meter. Nowadays, it is called as a net metering, right? Which is bidirectional. Normally, when we do not generate any power, that time the meter is unidirectional. Okay. Nowadays, also, when we are not generating any power, the meter which is connected at our home is a unidirectional because we take the power only from the MSCB. So it is unidirectional. But when we generate, we have our own solar generator and we export power to the MSCB. It must record that. So that meter which records in and out along with a direction change as plus and minus is called as a bidirectional meter or net meter. So whatever is the generated, okay, suppose our demand is more, then we use very less amount of energy from the grid. So only that much we are paying for. So this all records are maintained by a bidirectional meter which measures the energy. Okay. So when we have excess power, we can supply it to the grid. When we have less power generated and our load is more, we get the power from the MSCB. So this is the concept of import and export. So these are the details of the instrument. So inverter, as you know, you have done it in power electronics and drives. It converts DC to AC. So these are standalone inverters. So there are many techniques to improve the quality of inverter power. So generally PWM controlled inverters we are using. Then charge controller, it regulates the voltage and current from the solar cell, which is stored in the battery. It also protects the battery from discharging below the minimum level and charging above the maximum level. So that way it is increasing the life of the battery. And batteries, it stores the power So we can use it as and when required. Okay, so here we will stop today.